In this problem, we are going to look at the electric field at point P due to a one-dimensional contraption of two charges around P. And we're going to use that to determine that if an electron were to be at point P, how would it move or how would it accelerate? The first step is rather easy. All you need to do is find the electric field at point P. So we're going to go ahead and just say the electric field at P is equal to the electric field at P due to charge 1 plus the electric field at P due to charge 2. You see that, again, we're going to make right positive and left negative. We're going to say the electric field of charge 1 is actually making P go to the left. Not really making P go to the left, but if it were a test charge of a positive value, it would want to go to the left and attract towards negative charge. So we're going to see that the electric field due to charge 1 is actually a negative, since the field lines go in the left direction or negative direction. Now for Q2, we see it's a positive, and that's going to be to the right of P. But since it's positive, it's going to repel, so it makes P go to the left again if it's a test charge of a positive value. And so the electric field lines are, again, going to go to the left. So that makes this value also negative. So we have two charges actually helping to make stronger at point P, the electric field lines to look stronger at point P. So let's go ahead and run this out. Okay, again, I brought down the negatives and we just run out, or we expanded out the electric field equation for Q1 and Q2 with their relative distances from point P. Well, looking at the relative distances of 2 centimeters and 8 centimeters respectively, we have to put this into meters, so we definitely have to change everything into SI units here. That would be 0.02 meters here and 0.08 meters here, and then you have to square it. So this ends up being negative 561,875,000 newtons per coulomb for the first term, and then negative 702,34375 newtons per coulomb. If you add them up, this ends up being negative 6,321,09,375 newtons per coulomb. And if you want to get it into the proper SI significant figure unit, significant figures, you would go ahead and say it's negative 6.3, and the decimal place is moved over, I guess, 8, 1, 2, 3, 4, 5, 6, 7, 8 to the left. So that would be, in that case, E8 newtons per coulomb. This is for part A. For part B, we need to find out how this electric field affects an electron at point P and find out what the electron's acceleration will be. So what we're going to do is we're going to incite Newton's second law. Sum of all forces is equal to mass times acceleration. Again, we're going to use the absolute value sign so that we can take full control of the sign here. The acceleration is going to be net force over the mass. And due to the equation that links force and electric field, we have that force is equal to a charge value. In this case, it's the charge of an electron times the electric field divided by that mass of the electron. Doing the calculations, and you can see that the charge of the electron is negative 1.602 times 10 to the 19th coulombs. Mass is 9.11 times 10 to the negative 31 kilograms. And again, we're going to ignore all negative signs. So even though it's a negative charge, we're just going to ignore it because we know that the electrons are going to go to the right because it's going to be repelled by Q1 and attracted to Q2. So this ends up being a positive 1.1 times 10 to the 20 meters per second squared. Again, Yes, this will give you a negative if you don't have that absolute value sign, but we do already know that the electron is going to go to the left due to the situation.